Hello everybody. So these are the notes for 9.2. Let's see if I can get my camera going on here. There we go. So in the previous notes we were looking at, how to we were getting familiar with classifying differential equations and stuff like that, looking at their long-term behavior with the slope field, and we're looking at Euler's method. And, if you remember, Euler's method was used to approximate solutions, right? What we're going to do now in this section is we're going to solve differential equations. Well, we're going to solve specifically first-order differential equations. So, note. How do we solve a first-order linear ODE? How do we do that? How do we solve a first-order linear ODE? Well, we already know of one, right? This is the first kind we looked at. This is what? Separation of variables. Sometimes we can use separation of variables. Right? Sometimes we could separate variables. I don't know why this is doing this. I really don't. And we looked at a lot of different examples of that, even in chapter 7, which was like the first chapter we looked at. Separate the variables, integrate both sides, and boom, you're good to go. But in this case, we're going to look at a new type of differential equation. So I'll say this: there are other kinds of first-order linear ODEs, and these can't be solved via separation of variables. So there are other kinds of first-order linear ODEs which cannot be solved I'll just say via separation of variables. It just can't. A separable differential equation is a first-order linear ODE. It is. But as you're going to see in a moment, not every kind of differential equation like this can be solved this way. So the ones that we're talking about primarily, so if I am given a first-order linear ODE of the form, so I have dy dt equals a function of the variables t and y, right? So this is the basic structure of a first order linear ODE. Okay, So how am I going to solve this? Well, so the ones that we're interested in, first order linear ODEs, they take a particular form. And they can be written in this form. Don't worry about if you don't quite understand what this looks like yet. I'm going to go through it right now. So they're going to be written in the form dy dt plus p times t of y equals q of t. This is a first order linear ODE where p of t and q of t are continuous functions of t. So what that means is this stuff right here, so the p of t and the q of t, they're just expressions containing t in them. That's all they are. They're just functions of t. That's all they are. You know, they could be a number, they could be stuff with t in it, it doesn't matter, as long as they're functions of t. So I have dy dt, so here's the first order part, here's the first derivative of y, plus something with t times y equals something with t. And like I said, p of t and q of t, they could be functions of t or just a number. It doesn't matter. So if I have a first order linear ODE in this form, if I have it this way, separation of variables will not work. So this is the form that we're looking at. So in general, separation of variables will not work for this ODE. That's important. They will not work for this ODE. They will for, separable differential equations, which are also first order linear. But this is another type of first order linear where separation of variables will not work. So I have to use some other way to solve this. And before we look at that, I do want to make one mention of this. I do want to make a very important note of this. If you have a first order linear ODE written in this form, it's referred to, and you hear this a lot in a lot of contexts in math. This is called the standard form. That's called the standard form, and that's important. So if you hear someone, or like if you hear me or the instructions of a question saying, hey, put this first order linear ODE in standard form, this is what they're talking about. Put it in this form. It may not be given to you in standard form, but you will have to put it in standard form in order to solve it. And you'll see how we do that momentarily. Okay. So how do we solve this? So how are we going to solve this thing? What am I going to do? So there is a derivation to this, but generally what we're going to do is, and without going through the whole process of the derivation, which is kind of, it's technical and it's really sloppy, but basically what we're going to do is we're going to introduce a new function into the standard form. And this this thing we're going to introduce is called excuse me, it's called an integrating factor. So what we need to do is we need to introduce another function called an integrating factor. Let's call it integrating factor. All right, so what do I mean by introducing it, and what is an integrating factor? Don't worry if you don't know what that is yet. We're going to explain it. So what do I mean by an integrating factor? Well, to flesh this out a bit, it's a factor multiplied into the first order linear ODE that allows us to integrate. And this is, this is the bee's knees right here, guys. This right here is what allows us to solve these kinds of differential equations. So we're introducing an integrating factor into this function. We're going to multiply this integrating factor to both sides of this differential equation. And when we do that, and you'll see what I mean, when we do that, we'll end up getting something really nice over here, and something, we're not really interested in what we get over here. Well, not yet at least, but the good thing about doing this is when we introduce an integrating factor to the left side here, what we're going to get over here is going to be the product rule between two types of functions. And when we integrate a derivative, what happens? They cancel out. And that right there is the key idea to remember. So all right. So what does an integrating factor do? Let me simplify this. What does an integrating factor do? Well, it allows us, so let me say this, by introducing an integrating factor, and we denote this as, so this varies from textbook to textbook. It just depends on the textbook you're using. Every textbook is different. When I do it, I'm going to let the integrating factor, I'm going to use little u as a function of t. We're going to denote that as the integrating factor. So by introducing an integrating factor, denoted as this, and we'll talk about how we find it in a minute. By introducing this, so if I take this and like I said up here, I'm going to multiply it to both sides of my equation. What I'm going to get So if I multiply this by both equations in standard form, that's important, what you're going to get, what you get on the left hand side is the product rule. What's the product rule? It's the derivative of a product, right? So what you get is you get the product rule between the integrating factor U of t and y, which is the dependent variable. So here's the important thing you want to focus on here. Is you get the product rule between the integrating factor and y, the dependent variable. So integrating factor times y. And if you take the product rule of that comes, so when you find the integrating factor and multiply it by both sides, you'll see that the left-hand side is just the product rule between u of t and y, or the dependent variable in this case. And the dependent variable could change from problem to problem, but it's going to be, this is the dependent, this is the independent. And the integrating factor is the function that we introduce in here. And we're going to talk about how to find that very soon. So don't worry about that. Like you're like, all right, how do we find the integrating factor? What is it? So if I write that down here in so if I write that down in math notation, so therefore what I have is, so if I write this out, u of t times y, right, u of t times y, and if I take the derivative of that, right, so d dt, well, the derivative of a product is the product rule, so high d low plus low d high, so high times d low, which is dy dt, plus low d high. Well, the derivative of u of t as a function, which is a function of t with respect to t, is just u prime of t. So this right here is the product rule of this product, right? And you'll see what I mean when we actually go through examples, that when I multiply the integrating factor here to this side, you're going to get this. You're going to get this over here. So if I have this on here, when I multiply the integrating factor here, what I have is just this right here. So how do I get rid of this? Integrate it. And what will happen is they cancel out, and I'm just left with this. So therefore, this is what I have, right? On the left hand side. So when I integrate, I'll just say this to summarize: integrating will cancel the derivative part. So if I integrate this, I have the integral of this derivative. With respect to t, right? This is the integral part. This right here is the integral part. This right here is the derivative part. So the integral of a derivative cancel each other out. Now remember, the derivative of an integral is the fundamental theorem of calculus from Calc 1. But the integral of a derivative cancels out. So I'm just left with this right here. And that'll allow us to solve for y. So, you know, this might seem a little unclear to you right now, and that's okay. I'm just going through the whole process of how to solve this. And it'll make more sense. You know, usually when I show you examples, it makes more sense. But so before we do look at examples, though, we have to talk about how to find the integrating factor. So that's what I'm going to do on the next page. All right, so page 2. So how do we find the integrating factor? How do we find the integrating factor? How do we do this? Well, so if I have my first order linear ODE in standard form, so you got to get familiar with this. It's dy dt plus P of t times y equals Q of t. All right? That's my in standard form. This might seem redundant, but I'm emphasizing it. This is in standard form, so writing this is redundant, but so its integrating factor which we denote with U of t, is equal to, so this might seem a little obtuse, so I'm not going through the derivation of this because, like I said, it's really, you know, technical, but it's equal to e to the power, and in the power of e is going to be the integral of P of t with respect to t. That right there is the integrating factor. And I just want to make a note here. The integral of P of t dt may not be integrated at times. Since this is primarily Calc 2, most of the examples we'll see will have an integratable function here. But, you know, if you do take a differential equations course, you will see cases where P of t cannot be integrated. So what is P of t? Well, P of t, like this piece right here, what is that? What is it? It comes from here. It's this little piece in front of y of t. So whatever P of t is, you're going to pop that in this integral, e to the integral of that with respect to t, integrate it, and you're going to get, once you simplify that integration, you're going to get e to some stuff. Once you're done that is your integrating factor. You're going to multiply by both sides of this differential equation and then go from there. That's why it's important to put this in standard form, because if you don't have this in standard form, you won't be able to identify the integrating factor. Okay? So, you know, from here, so that's how you find the integrating factor. Alright, so we have everything we need to start looking at a few examples here. So let's do that. So, example. I'm going to start off simple. So solve the ODE dy dt equals 3y minus 4. solve that ODE. Well, okay. The first thing you should do is this in standard form. Well, before that, let me back up a second. Before that, could I solve this with separation of variables? Could I do that? You know, like I said in the notes, let me refer back to the notes here. In general, separation of variables will not work for this ODE. And this is a first order linear ODE. So if you add 4 to both sides and try to get y by itself, that's not going to be too easy. And you're going to get, you know, it wouldn't make sense to add 4 because then you're going to have dy dt plus 4, and there's no way to get rid of that. So separation of variables will not work here. So since this is a first order linear ODE, we could find an integrating factor. But before that, I have to put it in standard form. So put in standard form. So this is standard form, right? That's standard form. So how do I get it in standard form? I have dy dt plus some stuff times y. So here's that stuff times y right here, right? This guy right here is right here. So I got to get him to the left with the dy, with the prime part. So I got to subtract the 3y over. Okay. So I'm going to have dy dt minus 3y equals -4. All right. Is this in standard form? It is, because if you look here, I have dy dt plus, well, plus or minus, doesn't matter. Plus is the same thing as plus and negative. Okay. Stuff with t times y. Stuff with t times y. Well, remember, p of t could be a function of t or a number. I said that in the notes right here. P of t is a function of t or just a number. So, and this is equal to q of t, which can also be stuff with t or just a number. And so, you know, to compare this to this, in this case right here, this right here, so I'm including the negative with it, that right there is my p of t. And this right here is my q of t. All right? So, you know, just to set this against the standard form of a first linear ODE, you could see what is which. P of t is -3 and q of t is -4. So because of this, what's my integrating factor? What's my integrating factor going to look like? It's going to look like u of t equals e to the integral of what? What's p of t? It's -3. So it's going to be the integral of -3 dt. All right. So now integrate this. So I'll just do this on the side and then we'll go from there. So u of t equals e. What's the integral of -3 with respect to t? That's -3t. That's easy. So -3t. So this right here, that's my integrating factor. That's my integrating factor. What am I going to do with it? I'm going to multiply this to both sides of this differential equation. And it's very important that you realize you're multiplying this by both sides of the equation in standard form. Okay? So multiply, when I go through that, with the integrating factor. So when I go through that, I multiply this by everything over here. So e to the negative 3t times dy dt minus 3y equals, well, when I multiply negative 4 by e to the 3t, it's just going to be negative 4e to the negative 3t. So this is what I have now. Okay, let's distribute this in here. So I have dy dt e to the negative 3t minus 3y e to the negative 3t, and that equals negative 4 e to the negative 3t. That's what I have now. All right. All right. So here's what I want you to see. This is where the bee's knees shows up, man. So everything over here, this right here is the product rule between the integrating factor, which is e to the negative 3t, and the dependent variable, which is y. So if you're not convinced of that, go through the product rule. So, you know, high d low plus low d high. So high d low, there's high. What's the derivative of y? dy dt. There it is. Plus low, all right, there's low. It's right here. D high. This is the derivative. So what's the derivative of e to the negative 3t? Use the chain rule. Take the derivative of this, you're going to get a net factor of negative 3. Ah, there it is. Times the derivative of e to the negative 3t, which is itself e to the negative 3t. There it is. So this right here, so that's really cool. If you look at that right there, like go through this product rule. High d low plus low d high. High d low plus low d high. So if I write this out using, you know, just the product rule notation, so this right here is the derivative of e to the 3t, or negative 3t, times y. Right? Go through this. High d low plus low d high, and you get this back. Just go from here to here, and you'll see that this, the derivative of this, is what I have here. And that was found by introducing the integrating factor, which is what I said would happen. And that's equal to the right-hand side. So now, here's where the magic occurs. Since I have a derivative of a product, well, since, remember I said at the beginning of the notes, so we need to introduce another function called an integrating factor. What's the purpose of the integrating factor? It allows us to integrate. It allows us to integrate. So by introducing that integrating factor, right? So introducing this thing into here, I got the derivative of a product, and now I could integrate both sides of this equation. So when I do that, so let me go down to the next step here. So now I have the integral of both sides of my equation. So I have the integral of d dt e to the negative 3 times y, and that's respect to t, right, because it's an integral, and the integral of negative 4 e to the negative 3t with respect to t, right? I could integrate both sides, and what's going to happen here? The integral of the derivative cancel out. So this part, that cancels out. with this. And all I'm left with on the left-hand side is e to the negative 3t times y. That's the magic of using an integrating factor, and it's really cool. Now, you do have to go through this process, because this right here, this is where the magic takes place. And you can't just take this for granted and say, oh yeah, by doing this I could go through the blah blah blah. You actually have to see that this is the product rule here. If you do it correctly, it will be, but don't take it for granted. Go through the process and see it for yourself. You have to convince yourself that this is the product rule of this. So this is what I have now on the left-hand side, and that's equal to the integral of this function. So now from here, just integrate this, which we can do, and then solve for y. Okay, well, there's my left-hand side. How do we integrate this? Well, you could bring the negative 4 out if you want, but this is easy. E to the negative 3t, how do you integrate that? Well, this is going to come out as a reciprocal of negative 3, so that's going to be negative 1/3, right? Negative 1/3 times negative 4 is positive 4/3. So I'm going to get positive 4/3 e to the negative 3t plus c. Right? And now from here, solve for y. So how do you solve this for y? Divide both sides by e to the negative 3t. So now you're going to get y as a function of t, because that's what it is. Divide this by e to the negative 3t, so you're going to get 4/3. All right. Well, e to the negative 3t over e to the negative 3t, what happens there? It cancels out, okay? Plus, it's a plus sign, c over e to the negative 3t. So, you know, I'll have c over e to the negative 3t. And you could rewrite that if you don't like the negative exponent. You could rewrite this as 4/3 plus c times e to the, if you bring this up, make the power positive. So you could write it as that, 4/3 plus c e to the 3t power. So that right there is the solution that right there is the solution to my differential equation. Now, we are going to look at more examples of this, but I want you to realize something here. So, in this case, and I kind of alluded to this in the previous section, I have a constant here, c, right? C is a constant. Now, I can't find c in this case because in this problem I was not given an initial condition. Remember when we looked at Euler's method in the previous section? We were given a starting point, an initial condition. If I'm given an initial condition, I could find the value c here. So because I don't, what this is called right here, so this right here is called the general solution. Remember how I said the solution to a differential equation is a set of functions? Well, it's the set of functions where c could be any number. So c could be negative 10, negative 9, negative 8, and so on, right? All those values, and it could be, you know, it could be decimal numbers, it could be integers, it doesn't matter. C could be any number. So if you made c any number, all those different functions you get with that different value, that would represent all the functions that satisfy this differential equation. But if I wanted to find a specific function, I would need an initial condition. And remember, a differential equation with an initial condition is called an IVP, an initial value problem. And we're going to look at some. We're going to look at some. We're going to look at an example like that. All right, so let's look at another example. Solve the IVP. Solve the initial value problem. T times y prime plus 2y equals sine of t with an initial condition. So the initial condition is y. Come on, camera. Really? Y at pi equals 0. Okay, so, you know, this is the derivative, right? So I have t times y prime plus 2y. Now, I don't have it as dy dt, but y prime, same thing. I obviously can't do this with separation of variables. So what do I do? What do I do here? Well, so in this case, I have to, well, what's the first thing I should do? I got to put it in standard form, right? Is it in standard form? No, it's not. Remember, standard form looks like this, right? So I just have the y prime term by itself. It's not by itself. So what do I have to do? I have to divide through the whole thing by t. So when I divide through this whole diffie q by t, I get y prime plus 2 over t times y equals sine of t over t. So that's in standard form, right? Camera. Okay. All right, so now that it's in standard form, I have to find what's my integrating factor. Right? So, you know, just like I did earlier, this right here is my P of t, right? That's my P of t. And this whole thing is my Q of t. So now I have to find my integrating factor. What is it? What's my integrating factor? It's going to be e to the power, e to the integral of P of t dt. What is P of t here? It's 2 over t. All right, so how do you integrate that? Well, how do you integrate 2 over t dt? Well, you could bring the 2 out, right? You could write this as e to the integral, or you could write this as 2 times the integral of 1 over t dt, which is e to, so what's the integral of 1 over t dt? That's the natural log, isn't it? So it's going to be 2 natural log of t. But you could simplify this further. You could bring the 2 out as a power, right, because of properties of logarithms. You could write this as e to the ln of t squared, right? What happens to e and ln? They cancel out. Bring this out front. E and ln are inverses, so you're just left with t squared. So my integrating factor is an easy one. T squared. That's nice. So that's my integrating factor. So what am I going to do now? Okay. Multiply this by both sides, right? So I'm going to have t squared times the left side equals t squared times the right side. What am I left with? Distribute the t squared, so I'm going to have y prime t squared. T squared over t is just t, so I'm going to have 2ty equals t squared over t is what? T. So I'm going to have t sine of t. Alright? So this is what I have now. So again, what is on the left-hand side here? Provided I did my work correctly, and I think I did, what should be on the left-hand side here? This is the product rule between what two functions? The integrating factor and y. So I'm going to write that as the derivative of the integrating factor times y. And if you're not convinced, go through it. High d low plus low d high. You should get this. High d low. There it is. High d low. The d low is y prime. Plus low times d high. Well, the derivative of high is 2t. There it is. Bada bing. Beautiful. So now I could do what? Integrate both sides. Alright. The integral of t sine of t dt. Okay? So now this integral cancels out with the derivative. So I'm just left with t squared times y. And that equals the integral of the right side. Alright, so from here, like I said, this is the last part of the step. Now from here, you just got to integrate this and then solve for y and you're done. You'll have the general solution. But we need to find what c is, and we'll get to that. How do I integrate this? So, I really wish you guys could reply to this, but this integral we integrate by what? Integration by parts. Ha! We use integration by parts here. Woohoo! Remember those methods? Yep. Integration by parts. So I'm going to use parts here. All right. So how are we going to do that? So if we integrate by parts, so let me do that up here. Or, you know what, I'll do it here. So the integral of t sine of t dt. I want to integrate that. I want to get a result for that, right? Make your table, right? So d dt, integral of dt, plus, minus, and I'll write more if I need them. So remember, how do I use integration by parts? I have t times sine of t. Which one of these is going to give me the derivative? Well, which one of these, when I differentiate, is going to give me 0? Obviously t. So that means sine of t must go here. What's the derivative of t? 1. What's the derivative of 1? 0. What's the integral of sine of t? So again, if you're confused or if you don't remember these things, sometimes I forget them myself just because I have a little brain hiccup. But that's what I'm having right now. I can't even remember the basic integral of sine, which is negative cosine t. What's the integral of cosine of t? Well, that's sine of t, but I have a negative sitting out front, so it's going to be negative sine of t. Okay, so the result, the integral is going to be what? It's going to be, since I got 0, it's going to be this times this plus this times this. So when I write that all out, I get, so a negative times a positive is a negative, so I'm going to have negative t cosine of t plus negative times a negative is a positive, so I'm going to get positive 1 times sine of t, which is plus sine of t plus c. Okay, so that's my integral of t sine of t dt. So now if I go back to my original problem, I'm going to replace this with this. Right, so now I have t squared times y, and that equals, what do we get here? We got negative t cosine of t plus sine of t plus c. Divide both sides by t squared. So now here you're just solving for y. Right? So when you get that, you're going to get y as a function of time, or t, equals, so when you divide t squared by both sides, or all three terms, so t here cancels, so I'm going to get negative cosine of t over t plus sine of t over t squared plus c over t squared. All right, this right here is my general solution. But I'm not done. This was an initial value problem. I have an initial condition. So to find c, to find the constant c, apply the initial condition, which is y at pi equals 0. All right. So plug in pi here, and you're going to set, when you plug in pi for t, you're going to set that equal to 0. All right. So when I plug in pi, I'm going to have y as a function of pi. So I'm going to have negative cosine of pi over pi. Well, what's cosine of pi? Here's your calculator, right? Make sure it's in radians, which it is. So cosine of pi, or I'll do negative cosine of pi. It's not a big deal. Negative cosine of pi is, there's a glare, but it's 1. So I'm going to have 1 over pi, right? Plus, well, what's sine of pi? So sine of pi 0. So 0 over pi squared is just 0 plus, right, 0. So plus c, because I don't know what c is, I'm trying to find what c is. C over pi squared. And that's equal to what this was. It's equal to 0. All right, this is going to be equal to 0. So now just solve for c. So when you do that, so subtract pi 1 over pi from both sides, so you're going to get c over pi squared equals minus 1 over pi. You could cross multiply here, and you're going to get what? You're going to get c times pi equals negative pi squared, which means c equals negative pi squared over pi, which is negative pi. So that means c is negative pi. So I'm going to replace c with what I found it to be, negative pi. So my solution is going to be negative cosine t over t plus sine t over t squared minus pi over t squared. Because c ended up being a negative value, I could just make this minus pi. Minus pi over t squared. So this right here, so in this case right here, I found a specific value for c. So because I had an initial condition. So because of that, this isn't, so this right here is called the general solution because generally c could be any value. But here, because I found a particular value for c based on my initial condition, this is called a particular solution. So, you know, if you see problems like this on your homework, and you will, and on exams, and even on your packet, when they say solve the IVP, right, they're saying find a particular solution, because you're not only solving this to find the general solution, but you're applying the initial condition to find the particular solution. And that's it. So, you know, when it comes to finding solutions to first order differential equations or first order linear differential equations, that's the basic idea. So just to summarize, you know, these notes. When you have a first order linear ODE, put it in standard form first. Find the integrating factor. And then multiply both sides of the equation by the integrating factor. You get the product rule, integrate both sides, solve for y, and you'll get the general solution. And if you have an initial condition, you'll find the particular solution. And, you know, some of these problems could get a little lengthy. You know, this problem took up a full sheet of paper, almost. But, you know, this is Calc 2, so you're going to get lengthy problems. I don't think the process is that hard to follow. It's just, you know, it takes practice, but, yeah. So that's 9.2. So in the next section in 9.3, what we're going to do is we're going to look at applications of these kinds of problems. We're going to look at, you know, everybody's favorite topic, word problems. And we're going to look at what we call mixture problems. We're going to look at some real-life problems that can arise from these kinds of differential equations. So that's it for the notes for 9.2.